A major limitation of transplantation is the ischemic injury that tissue and organs sustain during the time between recovery from the donor and implantation in the recipient. Cryopreservation and storage of biomaterials at low temperatures provide a potential revolution for tissue and organ recovery, allocation, and transplantation. Although significant progresses have been achieved in this area, advances in tissue and organ cooling for cryopreservation have not been matched by similar advances in rewarming. Two technological barriers have proven difficult to overcome. First, the critical warming rates to avoid devitrification, the process of crystallization during warming, are typically an order of magnitude higher than the corresponding critical cooling rates. Second, these rates need to be sufficiently uniform throughout the material to avoid large thermal gradients, which produce thermal stress that often drives fractures or cracks within the tissue if they exceed the strength of the material. Utilizing nanoscale heating agents could provide solutions for these problems. For instance, induction heating of magnetic nanostructures can warm up the treated tissues or organs uniformly. And the photothermal conversion of plasmonic nanostructures can generate heat with extremely high rates. Furthermore, after integrating these two heating functions into one nanostructure, the dual-mode heating can further enhance the rewarming rate of cryopreserved tissues. Here, we will introduce a typical synthesis method of gold-coated iron oxide nanorods that can be powerful candidates for dual-modal rewarming. First, we synthesize the magnetic nanorods. 0.04 molar iron chloride is prepared and incubated at room temperature for 3 months, undergoing spontaneous acid-catalyzed hydrolysis. Iron oxyhydroxide nanorods, the basic template materials, was synthesized in this process. Attained iron oxyhydroxide nanorods are then treated with polyacrylic acid solutions for PAA decoration, followed by the coating of silica through classic Stober method, which is based on base-catalyzed hydrolysis of tetraethoxylane. Here are the reagents needed for the silica coating. And we will also use the vortex mixer and ultrasonicator to help with the mixing and reacting. First, we measure 20 milliliters of ethanol using the graduated cylinder and transfer it to the 50 milliliters centrifuge tube. Then we add 3 milliliters of water containing the iron oxyhydroxide nanorods using the micropipette. The mixtures are then mixed thoroughly using the vortex mixer and then placed in the ultrasonic bath. Next, we add 1 milliliter of concentrated ammonia to the mixture. The ammonia can provide a basic environment and help catalyze the hydrolysis of tetraethoxylane. Noting that it would be better to use the syringe to transfer the ammonia instead of the micropipette. Because high concentration ammonia is very volatile, it will damage the spring of the pipette, and the ammonia is easy to slip off, resulting in an inaccurate volume. After mixing well, 50 microliters of tetraethoxylane is added to the mixture using the micropipette. The hydrolysis of tetraethoxylane is then initiated, and the centrifuge tube is sonicated for 30 minutes to allow the coating of silica. After the reaction, the iron oxyhydroxide silica core shell nanorods are centrifuged out, and washed with ethanol and water thoroughly. The attained iron oxyhydroxide silica core shell nanorods are then treated at 360 degrees Celsius for 3 hours under a forming gas environment, achieving thorough thermal reduction. Magnetic iron oxide silica core shell nanorods are then attained. Aminopropyl triethoxysilane is then decorated onto the silica surfaces of nanorods for positive charge modifications. Nanorods modified with positive charges can then be decorated with negatively charged gold nanoparticles through electrostatic adsorption, by simply mixing the nanorods with gold nanoparticles. These adsorbed gold nanoparticles then serve as the seeds for following gold nanoshell growth. Seeded growth of gold shell was conducted by using formaldehyde as reducing agent and a prepared gold growth solution as the gold precursor. The decorated nanorods are then mixed with growth solutions containing gold chloride. Simultaneously, 3.7% formaldehyde solution is used as a mild reducing agent, and 5% polyvinyl pyrrolidone solution is introduced as the stabilizing agent. It is worth noting that additions of these reagents are divided into 19 rounds with 2-minute intervals. In this case, growth of gold can be effectively limited, leading to formation of uniform gold nanoshells. The growth structures of gold shells can be monitored using the TM. When only 1 milliliter of growth solution was added, the gold seeds only grew larger, but couldn't form a continuous shell. After adding 4 milliliters of growth solution, the larger gold nanoparticles coalesced and covered most of the nanorod surface, but it was still not a complete shell. When adding 12 milliliters of the growth solution, a continuous and complete shell was formed. The hybrid nanorods can then be used for the hybrid heating using both induction heating and laser warming.